Hi everyone, welcome back. I'm Prithvi, and this time around I have an interesting situation and a question for you. Imagine you are an NLP engineer, right? You're an applied machine learning engineer with an NLP expertise, mid to senior level, and you have done all kinds of training, pre-training and fine-tuning with GPTs to OPTs, and you're brimming with confidence. But to your surprise, the hiring manager walks in and says, we do have a pretty good applied machine learning engineering team with NLP expertise, and we have experience in training classical machine learning models from the scratch, and then doing some fine-tuning as well. But we are trying to take on something new. That is, we are going to be applying our models in sensitive settings. So we want to make sure that before our models are deployed, they are tested for bias, like social biases. So we want to have the ability for diagnosing models for social biases, measure it empirically, and then come up with one or more techniques for debiasing the models, and then measure it back again to see how much we are able to bring it down. And then finally, also we wanted to measure that how much the model's expressivity or the language modeling power has gone down because of debiasing, right? So if this is the question you are faced with, what will be your response? That's my situation and question for you, right? If you have answers for all these questions, first of all, you are in a tiny minority, and more power to you, right? Second of all, if you don't know these answers, don't worry, that's exactly what we're going to cover in this video, so buckle up. We'll go one step at a time, and then I have plenty of takeaways for you. So with that said, without further ado, welcome to the very first episode of a brand new series called Stuff You Should Know in Applied Machine Learning. Just to keep it briefly, why a brand new series, right? I have an isolated collection of tips and tricks of the trade for applied machine learning that I can give to you, which you can use on a daily basis, which does not have a theme or anything going on. They are completely isolated by definition, and they are worthy of 1 or 2 videos maximum. So I want to give it to you in a separate series without diluting the theme of vision language modeling series. We are doing it already. For those who don't know about vision language modeling series, it teaches you multimodal learning in vision language space from the scratch. I strongly encourage you to go check it out. So that's enough context, and that should set you up nicely for the rest of the video. So let's get cracking. Alright, so here is the agenda, and we will be doing it slightly differently, guys. As you can see, I've split the agenda into 2 sections. One is the concepts and intuition of the techniques, which I think you should understand deeply to be able to be an applied engineer who can do debiasing and diagnosing of biases. And then there is a step-by-step walkthrough. In the step-by-step walkthrough, I am picking a SoTA sentence transform model. I will also present a case why we need to pick up sentence transform. What is the case for sentence transformers to be diagnosed for bias? Just to give you a prelude, to my surprise, most of the studies are not actively researching state-of-the-art sentence transformers. That's one of the concerns. We'll speak more about it in a bit. As a part of the step-by-step walkthrough, we will be diagnosing the bias level in one of the sentence transform models. We will be measuring it empirically, and then we will be debiasing it. We'll be measuring again to see how much the bias has gone down, and then we will also present the case that if at all the debiasing techniques have sabotaged the sentence transformers, the quality of sentence transformers embeddings, right? And then we'll do some review of the results and some closing thoughts. So that's pretty much what we want to cover. But I just want to give you guys one more heads up that by any stretch of imagination, this is not a casual watch. You need to buckle down and focus and do it. There's a lot of information. It can be a very involved video. For best return on investment in your time, you need to focus. Yeah, just want to leave it out there. Right. So let's for those who are absolute beginners for the notion of a bias in language models, I would like to start with some definitions and some background, right? So what is a bias in language models? Bias is nothing but a shorthand for social biases. They could be historical, they could be contemporary, that can inadvertently leak into their language models actual power to model language, right? So the problem is this can be potentially harmful, especially when it is used in sensitive with settings like when you're trying to make decisions in a hiring setting or a financial setting or a legal setting, right? So this is I'm just trying to make a case that this is a pertinent, relevant problem. It's actively researched, and this needs to be tackled, right? And some of the most prominent techniques, some of the most prominent social biases which are intrinsically creeping into language models, which are studied actively, or like in that order: gender bias, racial bias, religious bias, and there are some minor biases like ageism, casteism, and other kind of minor discriminations. Nonetheless, they are important, and we have to tackle. So if you ask what contributes to bias, it can be data or it can be the algorithm. They are the two components which can contribute to bias. But data is the prime suspect. And for example, the infamous book corpus, which is used by Google in pre-training BERT and other models. There is an article called "The Dirty Secrets Behind Book Corpus." I've linked it in the references for you, and there is also a data sheet, like a model called. There is also a data sheet card for you guys for reading through. We will see more about it. While data is the prime suspect, data is not alone in this game. We cannot let the techniques and the algorithms, the techniques that the algorithms use, also off the hook. For instance, there is one of the prominent debiasing techniques is simply extending dropout for pre-trained language models. So the claim of the researchers is the models, some of the novel techniques like self-attention and some of the other self-supervised objectives can inadvertently learn some biases, and extending dropout and additional round of pre-training can bring them down. So there are multiple things we need to keep in mind when it comes to what can be the source of the bias, right? It can trickle down from several different sources. So that's enough background and definitions. So let's get started. But I just want to give you guys a teaser of what exactly you are going to be taking away. And when I say teaser, it is not the complete takeaway. I'm giving you a portion of the takeaway, and again, by definition, it's a teaser, so it's not supposed to make complete sense for you, and you will have a lot of questions, which is okay. So hence it is a teaser, right? So but still, I would like to give some context before we move forward. So what I'm showing here is under the section hours is a table that is showing that I've taken a SoTA sentence transformer and I've done a bunch of tests, right? The seat 6, seat 6b are all basically tests, and you can see what those tests means below in the description, right? So which seat 6 means it's actually a bias, it's particular bias of career versus family. This is basically a table which runs only gender bias tests, and individual tests means like male versus female, who is oriented to career, who is oriented to family, that, whether it is female or male, and then there is a STEM based biases. So all these things are ran for sentence transformers, and I've presented the bias in the form of certain numbers, and the number that we are using is called FX size. And if you don't, everything is going to fall in place in a moment, but I'll give you the definition. So for now, for the purposes of this teaser, understand that FX size is the metric that we're going to measure, and FX size has to be as close as possible to 0 for to represent lower, to indicate there is a low bias, and if it's higher, obviously there is high bias. And just as an information, guys, all these tests, in this case the gender, the hypothesis, the bias test has been run as hypothesis test, right? So now what do I mean by that is, so all these tests are taken. For instance, men versus women, who is career oriented, who is family oriented, right? In that test, the null hypothesis is there is no stereotype in the language model, and then we will try to run these tests to see whether we can reject the null hypothesis, meaning to indicate there is bias, or we will fail to reject the null hypothesis with a certain statistical significance. The statistical significance assumed here is 0.01. That means the test's p-value should be less than 0.01 to be rejected, right? So that being said, all these numbers in red with an asterisk in my results are basically statistically significant. Not only they are not closer to 0 to indicate there is bias, they are also statistically significant based on the level of significance we have chosen for the test, right? And also the green numbers in the second table shows that I have obviously taken a debiasing technique called INLP, and that has obviously brought down the bias a little bit, and we are also showing that the effect size metric has gone down by a number of 0.44, right? So again, don't worry if this is not making sense, it will all make sense in a moment. We will go, as we go forward, we will go deeper and deeper, right? So this is the takeaway, and I'm also comparing my analysis of a SOTA sentence transform model with a previous study somebody has already done on a BERT model, right? As you can see, a SOTA sentence transformer model has slightly higher bias when compared to a pre-trained BERT model. Just to leave it out there, this is not a from the scratch study from my side. Somebody has already done this, and this is, like I said, this is actively researched area. Somebody has done this research, and they have been diagnosing and debiasing pre-trained language models both in auto-encoding and auto-regressive space like BERT and GPT-2, but they have missed out sentence transformers, for whatever reason they seemed viable. So I picked up those techniques, and I have extended those techniques to study SOTA sentence transformer. That's context enough, right? So with this background and with this teaser, let's move forward and we'll understand the intuitions and concepts of the the different diagnosing techniques for social bias and then different debiasing techniques, right? So let's start with the intuitions of diagnosing techniques, right? So this will be a busy diagram, so don't worry about it. I have called out these blue boxes. For now, focus on the blue boxes for the key takeaways, and when you get the access to notebook, you can read them in detail, and feel free to explore as much as you can, right? So there are three prominent debiasing techniques or benchmarks available. One is called as encoder association test, and it's got two subtypes called word encoder association test wheat and sentence encoder association seat, right? Obviously, by definition, you can see, right, they are basically a benchmark for measuring the biases, diagnosing and measuring social biases in word embeddings and sentence embeddings, right? So and then the next one is stereo set, and then the third one is crowdsourced stereo set pairs. I'll go through quickly what is the big idea behind this data set and how they are proposing to measure the social biases in respective models, right? In encoder association test, both wheat and seed, the idea is pretty simple. So they will come up with two set of words or sentences. For now, let's start with words, right? Two set of words called target and attribute, target set and attribute set. For instance, if you look at it inside the blue box of the first column, first row, the words man, he, him is a attribute set representing the attribute of a male gender. Women, she, her represents the attributes of a female gender, right? And then we'll come up with targets, right? So for instance, the first target set is family oriented, family, child, parent, the things that I'm talking about, the things that are in dark brown. And then there are other set of targets like work, office, profession, right? As you can see, right, we are trying to come up with targets which is family oriented and career oriented. So what basically this test does is they try to somehow come up with a technique to measure whether one of the attributes, whether the male attribute or the female attribute is attached close towards either of the targets. If there is a skewness, there is a kind of a skew in attachment of either of the attributes towards a certain target, then that indicates the presence of bias. For instance, if you find that the female attributes are associated towards the family oriented targets rather than the career oriented targets, obviously that's a stereotype and it's a bias, right? So now this is what I've just explained is word level, and it is a word encoder association test. You can easily extend it to sentences, and that will be a sentence encoder association test. And as you can see that these are best suited for word embeddings and measuring biases in sentence embeddings, right? And there are other things like what kind of biases it covers, whether it is explainable or not. As you can see, since we are using attribute set and target set, it's pretty explainable. It's not a black box as to how it came up with the bias, the measure of the bias and things like that. I would encourage you to check out the paper. And like I said before, the test that I showed you, the results that I showed you in the preview is the result of seed test. Hence, we are using the same effect size as the measure. Next is an interesting data set called stereo set. Again, focus on the blue box, right? The idea is to come up with a template with the completion. For example, our housekeeper is a mask, right? When you mask it, and then this data set basically has 3 sentences for each template, right? For example, one which is stereotypical, like the one which I'm showing in the red, and then the one which I'm showing in the black, that is our housekeeper is American, and then the third one, our housekeeper is a computer, completely irrelevant, right? So we have 3 pairs of sentence per template. One is a stereotype, harmful, one is a anti-stereotype or harmless, and one is completely irrelevant, right? So what they calculate from this is 2 matrices. One is called stereotype score and one is a language model score. Let me explain what are those, right? Stereotype score is basically, I've given those definitions there, but I'll articulate it once for you. The percentage of examples in these templates that are strongly associated towards the stereotypical association, as opposed to the percentage of examples that are associated with a stereotypical association as opposed to anti-stereotypical association is measured as a stereotypical score, stereotype score. Now, what do I mean by that is, if you take a BERT model, we'll try to make these masked templates, we'll try to get the completions and try to see how much it is completing in a stereotypical fashion, how much it is completing in an anti-stereotypical fashion, and form the ratio. That is a stereotype score, and obviously we can see the more it is associated with stereotypical completions, the more biased the model it is. It is like perfect for autoregressive models like GPT-2 and GPT-3, and also masked language models like BERT and cousins, right? Again, this is since it is very explicit, it's a glass box, and encourage you to check out the paper. And the third data set, benchmark and data set is called crowdsourced stereo pairs. And unlike stereo, it is very similar to stereo set, where we are trying to get some completions. But unlike that, what we have is only two sentences. That's a pair, which will have one will be stereotypical and one will be anti-stereotypical, or which violates the stereotype. I've given examples. Like for example, people who live in trailers are alcoholics, based on it's a stereotype based on socioeconomic background, and then we are violating it by saying that people who live in mansions are alcoholics, right? So one metric that we are measuring from here is called stereotype score, and the idea is to get the when it is completing, when the model is trying to come up with the completions, or the model is trying to make those token predictions, which one is getting a higher token predict probability, the stereotypical version or the anti-stereotypical version, right? So that's how it is calculated. Again, it's a glass box, and it's suited for autoregressive as well as mass language models. I strongly encourage you to check out the paper, and that's pretty much the summary of the diagnosing techniques. 3 prominent diagnosing techniques. Once you get the notebook, again look at the table one more time and explore as you see fit. Right. So moving on, I've given you some examples, just so that you don't have to imagine, right? Like, let's take an example of gender bias in a seed scenario, that is sentence encoder association test, right? As you can see, we have attribute and targets, right? So target basically says like, John and Amy are 2 male and female names, and the executive and parents, right? Basically, those attributes are saying that who is associated to family and who is associated to career, like I explained in the previous table. So we will try to see if John is associated to executives more and Amy is associated to parents more, to see that if there is a career versus family oriented bias existing in a particular embedding of a model, right? In this case, a sentence embedding. And stereo set examples, I've given an example. I've given an example. Like I said, there will be 3 sentences: one stereotype, one anti-stereotype, and one will be irrelevant. And then we'll try to measure 2 things. So feel free to go through these examples to make sure that your understanding is solidified. Okay, let's move on to the intuitions in the debiasing techniques, right? So again, this is going to be even more a busy diagram, so feel free to explore this table as much as you can when you get access to the notebook. I'll try my best to cover as much as possible, but the idea for me to show you this table is not to overwhelm you, but to give you the big idea and to introduce you to the larger picture. But for the practical purposes of this exercise and this notebook, like I said before, we'll be picking 1 or 2 diagnosing techniques and 1 or 2 debiasing techniques, right? But still it is worthy to give the intuitions and concepts behind these techniques, right? The first one is called, there are 5 debiasing techniques, and each of them are suited for different styles of language models, and they do debiasing at different levels. Some of them are training aware or at pre-training level, and some of them are post hoc, meaning they don't do anything to the actual parameter of the model itself. They will take the output of the model and then they play on top of it. And some of them are glass box, and some of them are black box, and so on and so forth. The first one is called counterfactual data augmentation. As you can see, the counterfactual data augmentation involves basically rebalancing the actual corpus, right, by swapping the bias attribute. Now, what do I mean by that, right? For example, if you have, if you take a Wikipedia corpus and extract sentences for male and male-oriented sentence and female-oriented sentence, and then, like I've highlighted, the doctor went to the room and he grabbed the syringe. Instead of the male-oriented pronouns, replace them with female-oriented pronouns, and then get a lot of sentences, and then you basically run an additional round of pre-training. This is very suitable. This is very well suited for all kinds of vanilla pre-trained language models. Like I said, it will change the parameter because we are doing an additional round of pre-training, right? And the next one, like I mentioned before, the argument of the dropout debiasing technique is some techniques in algorithms, like the most modern self-attention and few other self-supervised objectives, have a tendency to learn some inadvertent biases. So if you increase or play with as a hyperparameter, play with the dropout at attention level, both at the pre-training level, if you do some kind of extra dropout, play with the dropout values, it apparently proves to reduce a certain kind of inadvertent bias, especially gender bias. The study showed that especially it is suited well for gender bias, and it's suitable for all kinds of vanilla pre-trained language models where we have to where we can do an extra round of additional round of pre-training with the different values of dropouts. As you can see, this is like shooting in the dark. This is like there is nothing glass box or white box about it. You will be trying different values for dropout, and what comes out and what is actually mitigating bias is something that you cannot control or understand or explain. So hence it is black box. And there is another technique called self-debias, which is basically a post hoc and black box because it is nothing but coming up with handcrafted prompts for models like GPT-3, right? You come up with different prompts to make sure that the model is first generating discriminative text and then mitigating the discriminative text, right? So feel free to check out the paper and description for that. Obviously it is post hoc, so it does not play with the parameters of the model. Those three are so the three techniques that I spoke about, that I introduced, are interesting, but much more interesting for our conversation and more relevant for sentence transformer context are Sentence-Debias and something called INLP, or Iterative Null Space Projection. Both of them are projection based, and I'll explain them not just with the textual, but also visualization much more in much more detail, because those are not only relevant, those are very interesting, and they are apparently Sentence-Debias, according to a certain study, is the most is the best performing debiasing technique that is out there, right? And I've just also called it out as aggressive, and I'll tell you why I'm calling it as an aggressive debiasing technique, right? So rather than going through the text, let me give you a visualization of iterative null space projection, and then we'll basically go deeper on that, and then I will cover Sentence-Debias. Even though the order is different in the table, we'll go through INLP first, right? I hope the diagram is you guys are able to see it. It's big enough, and so let's as you can see, there are two phases to this iterative null space projection. There is a first phase on the top where we created a debias space, right? Now let me explain what do I mean by that is, right? So the idea is to basically come up with use a large corpus like a wiki text or something like that. Come up with gender oriented. I'm giving an example for coming up with a debias space for a single bias type. So it will be much more easier for you to understand, because we have different kinds of biases: race, religion, and gender. In this example, assume that we are talking about a gender bias, right? So what we are doing is to use a corpus like wiki text and come up with gender oriented examples, right? Or extract gender oriented example like male sentences, female sentences, and neutral sentences, and then use a particular model, right? Like for instance, in our case, use the sentence transformer to come up with the embeddings or representations, right? Once you come up with that, take those representations and then take those representations and train a classifier, right? Let's talk about one classifier, and I'll tell you why we need more than one classifier as shown in the diagram, right? It could be it's a linear classifier. Feel free to picture anything, like from as simple as logistic regression or SVM or anything. In this case, the researchers have picked up an SVM model, right? So SVM is an algorithm, right? So the idea is to come up with a linear classifier which will classify all these representations for the respective labels, meaning our data set knows what are the male sentences, what are the female sentences, what are the neutral sentences, right? How about coming up with a model which learns to discriminate between male, female, and neutral, right? Once we do that, then we get something called as the null spaces of the weight matrix of the classifiers. That is definitely confusing, and I'll explain it, right? For now, just assume that there is a process. Let's say you know what is a null spaces, and then we take all you need to know here is we take the weight matrices of the individual classifiers and get the null spaces of the individual classifiers, and then some way, shape or form combine those individual null spaces to form a subspace, right? So the subspace is nothing but a degendered subspace, or the subspace which has no notion of gender, right? Now what we do is you can use this subspace to project all your sentence transformer embeddings to come up with the debiased representation, right? So now what will be confusing for you is what linear classifier does, how do we come up with the null spaces for it, what a null space is even, how do you combine those null spaces to form the degenerate subspace, and how do you project. All this is going to be confusing for people who don't have any introduction to linear algebra, or even for certain applied machine learning engineers. Don't worry, we'll fix it, we'll cover that, right? A quick primer is, let's talk about what is even a null space, right? Forgive me if my handwriting is not very clear, I've tried my best, right? If you have a matrix, again focus on the blue box. If you have a matrix A, like I've shown a 2-row 3-column matrix, the null space of a matrix A is nothing but a column vector which can make the result of the matrix multiplication as 0, right? Digest it for a minute, right? That's the null space. I've also given an example below in red that for the matrix that I've given as A, -7, 2, 1 is a column vector which on multiplication gives you 0. So basically the formula is null space of a matrix is nothing but a vector that can give you 0 vector, that Ax is equal to 0, right? Now we understood what a null space is, right? So why we need that? It's a classic way of learning to unlearn, right? So I just explained you what a null space for a matrix is, right? So let's now recollect the idea of taking the weight matrix learned by the individual classifiers, right? Every classifier will have a learned weight matrix, right? So imagine now we take the learned weight matrix, and what does it have? the weight matrix basically has learned to discriminate between male, female and neutral. So that means the decision boundary it has learned is helping to discriminate between the genders. So coming up with a null space or a column vector which will make the weight matrix of the classifier basically obliterates or destroys the decision boundary. You guys are understanding? We are trying to understand or extract the elements that can help us to unlearn the gender discrimination from those individual classifiers, and those are nothing but one or more column vectors. That is for one matrix, right? So now let's go back to this diagram. Now not only we have one linear classifier, we have multiple linear classifiers. Now imagine taking the weight matrix of each and every classifier and coming up with its null space. That means the column vectors which can make it 0, right? Then what we do is we do the intersection of those null space. We know what a null space is right now. Since we have multiple classifier, we will have multiple null spaces. We will do an intersection to form a matrix called as projection matrix that forms your subspace. The subspace is nothing but a projection matrix for all practical purposes. Projecting a sentence transformer sentence embedding on a subspace for all practical purposes is nothing but coming up with a projection matrix and doing a matrix multiplication on top of it. In terms of an operation, that's what we are doing, right? So what does that projection matrix signify is ability to unlearn the gender discrimination from the embedding. So for visualization purposes, I've given you that a sentence embedding is having the red parts indicate the bias, and as you can see, once you project it over the subspace, we have the red parts are gone, which is purely for visualization purpose. Don't misunderstand thinking that only certain dimensions will encode biases. It's not like that. It's pure number game, right? It can be anywhere, it can be hidden anywhere, and the subspace has the ability to basically, when you project on the subspace, it has the ability to destroy or remove the gender discrimination. This is in context with a particular bias type, which is gender. We can easily extend this idea for racial bias, religious bias, or any kind of bias, as long as you can come up with a nice data set of sentences where you can build some classifiers, and from the classifiers you can extract null space and construct the projection matrix, right? I would like to spend some more time on this. I want you guys to understand that this is a very interesting technique, right? I want you guys to go back and check out the quick primer on null space example here. This is pretty simple, and then see what we are trying to do with the null spaces and what they are good for. Null spaces are nothing but elements which help us to which are basically helping us to unlearn, right? So this is why it is called iterative null space projection. We are not only getting null space from one classifier, we are iteratively doing it on multiple classifiers and getting an intersection of all the null spaces. Hence the name iterative null space projection. Take your embedding and project it on a null space. That's the idea. So the projection will give you a debiased vector. So another technique we spoke about is called as Sentence-Debias, right? I also told you guys this is also a projection based technique, but it is slightly different. Let me explain, right? This is why I'm explaining this in relationship with INLP is, now that you have a good hang of iterative null space projection, it is easy for you to extend the idea to sentence bias. This is also projection based, but as you can see, it is slightly different. Do the same thing, like use a corpus like Wikitext, come up with, again we are sticking to gender debias, guys. So come up with male, female and neutral sentences, use the same sentence transformer model to get the representations. From the representations, apply principal component analysis, take k component, which is a hyperparameter, to form the k important vectors, right? Use those to form. So what we are trying to do is, the principal component analysis will give you the most significant part of the representation. What is the significant part of the representation? If it is bias, those are the components which contributes to the bias, right? Now, in the last technique, INLP, we formed a subspace which is degendered subspace, right? Now what we are trying to do is exactly the opposite. We'll come up with a subspace which is biased, which contains actually the bias using PCA, right? Once that is done, if you apply the sentence transformer embeddings to it, it will directly get, if you project it to the bias subspace, we will get a representation which highlights the biases, right? So what we are trying to get is highlight the subspace and get a representation, and then the final step is you take the original representation and subtract only the biases to get a debiased representation, right? Let me go through it one more time. Instead of INLP's technique to come up with a degenerate subspace, we are coming up with a bias subspace and then highlight the bias. We get a representation of the bias separately. We get the original representation of the sentence transformer, right? And then we subtracted both to get a debiased representation. So these both are nifty in their own way, and apparently, like I said, Sentence-Debias is much more performant when compared to INLP as per the previous research. So these are the two techniques. Now you understand, right, why these techniques are called aggressive, because we are aggressively trying to unlearn the ability to discriminate male, female and things like that. So we don't know if we are going to so aggressively remove all kinds of notions between male, female and neutral, what kind of negative impact it can have in a model's ability to understand gender at all, right? So we don't know. And also what we don't know is how much it's going to affect the model's sentence embeddings quality, right? Because it's really obliterating the decision boundary and we are collecting to form subspaces and projecting, right? So those are the two things we need to keep in mind as to why I'm calling them as aggressive, right, in this 5 techniques. And the same thing that I explained in the visual is in the table. The steps involved are also the verbal version of the visual, and the data set used is wiki text from the Wikipedia, right? All right. So moving on, now we have what we have covered is the intuition and concepts behind the diagnosing techniques, and we have moved on to debiasing techniques. For debiasing techniques, I have given you some visual explanation of 2 prominent techniques which are very pertinent and relevant for sentence embeddings. And now the next logical step is for you guys to see, why I'm harping on sentence transformer, what is the motivation, why you want to do this, right? That's actually a fair question for anybody to ask, right? So the first thing is, guys, you need to understand it is not a debatable thing, or it is a very well documented stuff that even concurred by the author of a BERT model, saying that sentence embeddings from a vanilla pre-trained BERT model is really not a high quality embedding, right? The whole research of sentence transformers by Reimers is basically because of the lack of quality in the sentence embeddings. This has been proven, right? Now, if all the previous research that has been done in diagnosing and debiasing bias, including the research I am citing in this notebook, has taken vanilla pre-trained models for getting sentence embeddings to test biases, right? Test for biases, right? So below table here clearly shows that even an average of glow embeddings perform better as a sentence embedding when compared to vanilla BERT embeddings, right? That basically shows the quality of sentence embedding is really lousy when it comes to vanilla BERT, right? So all the previous research and the research I'm showing here have taken an average mean pooling of BERT embeddings. I don't think they can be a good representation of sentence embeddings, and I don't think that's a good way to measure the indication of bias, because if they are, after all, they are lousy sentence embeddings, they may not have a good representation of the semantics of the sentence, so they may not have good representation of the bias encoded in there itself, is my argument, right? So and another surprise is none of the previous researchers are actually even considering sentence transformer, even though sentence transformers are having an additional round of it's still a pre-trained model. It is having an additional round of testing with a different loss function and a different objective, but still they are proven to have high quality, elegant sentence embeddings and widely adopted, and to me it makes sense to study them. Also, another worthy point that you need to notice is, let me show the results again that I showed you in the teaser, right? So BERT model is a vanilla BERT model, which is BERT based uncased, right? 768 dimension model, right? But the SoTA sentence transformer I have picked up is a much smaller model. When I say much smaller model, there's a compression done on top of it, and also and also possibly some kind of dimensionality reduction has been done, because their dimensions, the hidden dimensions, are not 768, they are 384. But as you can see, right, in spite of the fact that it is such a small model, it is distilled and compressed, and it is also dimensionality reduced, still it is having a higher level of bias compared to its a vanilla equivalent BERT, right? So that is concerning, and it's something that is supposed to be that warrants for a study, right? So, and also we can, if you have to guess, we can lay it all to the data that has been used to train the further pre-train the sentence transformers. Reimers, who is the author of sentence transformers, has given in the model cards and Hugging Face page that they have used 1 billion pairs, and I've included a link to that, and I've also shown what are the different data sets used. We will go through that in a moment, but just to close it up here, this is the motivation, right? So sentence transformer makes a lot of sense to be studied, and these are some of the explanations, right? Moving on. So I'll also give you an empirical example as to, if somebody is asking why prove me that sentence transformer embeddings are of high quality. Don't just tell me verbally. If somebody is asking, there's a simple way to prove that, right? Although lots and lots of sentences are required and you have to do a larger study, but I'm just trying to show that the quality of sentence transformers is much higher, and they are very, very good for downstream tasks, right? So for that, I've just taken a vanilla BERT base uncased and took two sentences, come up with the embeddings in the same way sentence transformer is coming up with embeddings. Like by default way it is doing is mean pooling, right? So, and again using the SoTA sentence transformer model, the same model that I showed you before, the mini LM L6V2, using mean pooling, and I'm taking the same set of sentences and comparing the embeddings similarity, like a pair of sentence, come up with the embeddings and then calculate the similarity, right? So what I'm doing is, first pair is two almost similar sentences, are pretty close in terms of semantics, and then another pair which are completely different, right? So what you can see in the results is, when the sentences are similar, vanilla BERT is very, very optimistic, and it gives 92% similarity. The SoTA sentence transformer, in spite of being a high quality sentence embedder, is only giving 82. It might look disappointing for you, but hang on. But what happens is, the quality of the sentence embedding is only visible only when the sentences are different, right? When it is different, just look at this example, right? I've said that the first sentence is I'm looking for an apartment in London. The second sentence is I'm looking for a zoo to donate my pet lion in London. Completely unrelated, right? So if you see, again, vanilla BERT is still optimistic and it's giving almost 82% similarity, which is completely unacceptable. But look at SoTA sentence transformer. Now it is able to understand there is no similarity and it's like less than 50%, right? So if you guys want to prove with a simple example, you can always say the quality is readily apparent only when the sentences similarity diverge semantically. You can show that the sentence transformers really shine there. So that's one example I want to show, just to buttress the fact that why I'm picking sentence transformer and why the qualities are not so lousy when compared to vanilla BERT, right? Next is the step where we want to, like I said, right, we are going to pick up one particular bias for the purpose of this exercise and diagnose the bias on the model we chose and debias it, right? So by the way, guys, I have, like I said, none of the code is done, none of the research is done from the scratch by me. I've taken the bias bench that the previous researchers have done and forked it, and it is not a trivial change. You have to actually do a lot of changes to make sure that it is supporting sentence transformer. I've done exactly that, but make sure that the original path is still intact. That means you can still use the original repo for vanilla pre-trained models like BERT and GP2, but also you can use it for sentence transformer. I'll give the link to this. I mean, it is in the closing thoughts. And there is one more repo I had to use for this. I will talk about it in a minute. Just hang on. So what we are doing is we are just cloning the fork of the bias bench, and The first step is diagnosing, right? They have given scripts, and I have also given clearly that how to run these scripts here. As you can see, extending bias bench for sentence transformer and how to run these scripts. So you have multiple sources. The steps are available in the GitHub repo README, as well as it is available in the notebook, and I'm also talking through it, right? The first step is the diagnosing technique or the benchmark we are using is SEAT, and the model we are going to use is the SoTA sentence transformer, which is mini LM L6v2, and by default we want to run 100,000 samples, right? So like I said, recollect what SEAT does is it does tests as hypothesis testing, right? It takes different samples, and then I've told you, like, it comes up with the embeddings from the model we have given, from the designated model, calculates the embedding, and then figures out the effect size. Remember, the effect size is basically trying to find out if a particular attribute and a target is closely associated to represent a stereotype or not. There is a bunch of tests. I strongly recommend you guys to go back and check out the data. For example, if I open the SEAT, you can see, right, there is an angry black woman stereotype, there is a competency based stereotype, and there is a religion stereotype, race stereotype, and all that. But remember, for our exercise, we are not looking at all the biases, we are looking only at gender type, right? So if you look at this, as you can see, right, each of the tests are constructed as a null hypothesis, and then it is calculating the effect size, calculating the p-value. If the p-value is less than the significance, obviously it is statistically significant, and if it is not, remember, effect size has to be close to 0 for indicating there is no bias or less bias. Right? It's pretty straightforward, guys. I want you guys to check the SEAT code in the repo and how I have changed it to support sentence transformers. And just to show you one more thing, this you have different kinds of switches, right? For example, you have different options to run only certain tests, right? Like they accept the list of tests, right? If you are interested only in certain tests to run for diagnosing, you can run only them. For example, you want to run only for gender, you can pick and choose. For our case, I just ran everything, but even though our focus is only gender, yeah, I feel free to go through this, guys. The next step is we have now, what we have done is we have diagnosed and measured it. Now we are going to do is use one debiasing technique, and we are going to apply the debias on top of the sentence transformer we have chosen, right? Now let's recollect the technique. The choice of our debiasing technique is INLP. So recollect the idea of INLP. We are going to create some data set which can tell us what is male, female, and neutral. We're going to calculate the representations from the model we have chosen, come up with classifiers, classify, get the null space, form a projection matrix, and then project it on, and then we will project the sentence embeddings on the projection matrix to calculate, to come up with the debiased representations. Remember, the idea is to get the projection matrix, which is the subspace, right? So as you can see, I have used my version of, the Wikipedia text is required. Like I said, right, the source data that is required to come up with the male, female, and neutral sentence is Wikipedia 2.5 text. It is available as a part of the GitHub repo. You can download and put it in your wherever you want to put it and bring it down. Once that is ready, you can just directly run the code called INLP projection matrix. Again, I have to change it to support sentence transform. There are a bunch of changes. Please feel free to review and compare with the original report to see how much it is different and so on and so forth, right? So once the projection matrix is calculated, once the projection matrix is calculated, it will be stored in this location, results projection matrix folder inside your bias bench. So feel free to save it, right? So in the name, for example, projection matrix can run only for a particular bias type. You cannot run it like we have run the diagnosis part for across biases. You cannot run it across biases. It runs only one bias type, because you cannot mix and match the null space, right? So you'll have to run this code, INLP projection matrix calculation, for a particular bias of your interest. In this exercise, we are going to run it only for gender, and then obviously you have to give the model the base model which you want to do the projection matrix based on, right? Once that is done, you have now the projection matrix. So what you have to do is you have to debias, right? So how are you going to debias is use the projection matrix and project the embeddings for different seed tests on top of the projection matrix to come up with. So which is pretty much taking the same set of tests, right? In our now, like I mentioned, you can run selective tests, right? When we diagnosed, we ran all the tests, but since the projection matrix we created is only for race, we are going to run only for the race test, which is the list of, you can pass the list of race tests, recollect the list of race tests from the takeaways, that is seat 6, seat 6B, seat 7, 7B, 8 and 8B. These 6 tests are the most prominent gender based tests in seat, right? So that's exactly what I'm passing here once the projection matrix is available. So what we are doing is we are calling the Sentence-Debias code in the experiments, same 100k sentence, but the list of tests is restricted only to the 6 gender based tests, and obviously we have to give the path of the projection matrix, right? The projection matrix which we just created from the last step. Once that is done, as you can see, right, this also does the same thing, right? Same thing like seat, but it is using the projection matrix to come up with the similarities, but it also calculates the p-value and effect size and so on and so forth, right? Feel free to go through that, guys, and once, yeah, let me just go through seat debias. It's gonna do, again, like I said, right, it will have also all kinds of knobs for you to pass certain tests and so on and so forth, and there will be a place which will basically use the projection. This is the portion where it is accepting the projection matrix path as the keyword argument, and then it's using it here. This is the point. You can check out the code exactly as to how it is using the projection matrix to debias, projection matrix as subspace to debias the sentence embeddings, right? So the result here, now it should make sense as to what we are talking about in this table, right, guys? So if you look this table back again, so the seat 6 to seat 8B are all the 6 gender based tests, and the effect size average is the absolute average of all the numbers, and the first row in red is basically showing our diagnosis on top of the model, right? And what are the respective effect size and what with respect to the level of significance in terms of statistical significance, right? And then we have applied INLP to measure the same numbers for the same test. So once we apply INLP, that means if we debias using the projection matrix and run the same tests on same sentences, what are the numbers for the respective tests? That's what the second row in green shows. And the average effect size has gone down by 0.44. Now we understand, right? It used to be 0.96, and INLP has definitely helped in debiasing the gender bias for this particular sentence transform model to a certain extent, and the level to which it has gone down is pretty significant, right? So in terms of sentence debias, I've given a question mark because I've given the intuition and the code is available for you guys. It's one of the exercises you guys can pick it up, and you know the intuition, just extend the idea to debias the same model using sentence debias technique. I'll leave it to you guys, right? So that's one thing, but I did not only show, even though the cells for the code that I ran shown only for the gender debias, in terms of results, I'm also capturing the race bias diagnosis and the debiasing part, as well as for religion, right? For the same sentence transform model, for race wise, if you see the average effect size and the INLP's value, it is actually not helping, and if you see the original paper, it is pretty consistent. So INLP is a pretty good debiasing technique when it comes to gender biases, but when it comes to racial bias or religious bias, it is actually not useful, or in a very minor way it's actually harmful, because as you can see, INLP is increasing the effect size a tiny bit, like 0.02, and religious bias like 0.05. It's minuscule, but still it is nonetheless, it is not helpful and it's slightly harmful, right? So if you want to understand what are the different racial tests we are doing, here is the description. Feel free to go through that, the racial descriptions. This is the description of the gender tests. racial test, and this is the religious test. The religious test is pretty straightforward. We have anti-Islam, like Islamophobia test, and anti-Semitism. Right. So now what we have covered is the actual walkthrough of how to use the bias bench code that I've changed to adapt for sentence transformer support, step by step to diagnose and measure, and then pick and choose a particular debiasing technique. In this case INLP, probably create a projection matrix and then debias and present your results, right? So now what we have done is we have now shown that, hey, we know how to measure bias, different kinds of social biases, and quantify it and measure it and represent a number, and then we can also pick and choose a debiasing technique, and we also measured the results after debiasing. But what is sorely missing is, since INLP and Sentence-Debias are projection based and also very aggressive by definition, how much it is affecting the sentence quality, the quality of the sentence embeddings the transformers can produce, right? That's something we need to understand. So that's our next logical step, right? How does debiasing using INLP affect the richness of the model representations, right? I'm going to demonstrate this in a couple of different ways. One is using like I showed the sentence similarity example before to show why the vanilla BERT sentence quality is, sentence embedding quality is lousy. Similar thing we could do. So one is vanilla sim score. That means take the sentence transformer model, come up with the embeddings for 2 sentences, and then calculate the similarity just as is. And then the next version is a debiased similarity score, meaning take the same model, same sentences, come up with the sentence embedding, but apply debias and then calculate similarity score, right? So feel free to check out the code. It's pretty straightforward, but the results are here, right? I'm having 2 sentences. I would like an apartment or a condo in central London. I'm looking for a place to stay in London. They are kind of semantically similar, right? And then as you can see, the biased version is 0.73 and the debiased version is 0.7. As you can imagine, right, we have, in the name of debiasing it, we projected it over a subspace. So we clearly have diluted the model's ability to capture rich semantic representation, but it is not so bad, right? For example, think about this, right? When you compress models, whether we are distilling or whether we are quantizing or whether we are using mixed precisions and so on and so forth, usually we trade off some level of accuracy or some kind of metric of your some desired metric, right? The model usually goes down. So this difference from a bias model's representation similarity of 0.73 to 0.70, in my opinion, is actually acceptable and minuscule. It is not, I would say, it does not drastically sabotage the sentence quality of the embeddings, right? So that's one way of representing. The another way of representing is actually calculating something called as a language model score. Intuitively speaking, language model scores are relevant for autoregressive models, where you can calculate the you generate a sentence using GPT-2 and then you come up with the token probabilities. But how do you do it for a mass language model? Like, so the sentence transformers are BERT like MLMs. So there is a prominent paper called as mass language model scoring, which calculates this, calculate the pseudo log likelihood. Okay, no, it should not be PPL, it should be PLL, pseudo log likelihood score, right? So feel free to check out the paper. Here is the link, and the intuition is shown very simply in this visual, right? So what they do is, for a given sentence, they try to mask one token at a time and then calculate the token probability for the masked token and then try to get a log likelihood, summation of the log likelihoods, that is PLL, right? So it's a pretty simple idea, and there is a library already existing for that as well. So like our bias bench, this MLM scoring is also available. Apparently they don't support sentence transformers, so I had to change sentence transformers and also inject the code for supporting debiasing, right? Because they will calculate, even if we extend it to support sentence transformers, they can only calculate the MLM score for a vanilla model. How do you inject the idea of debias? That needs to be done. So those are the couple of changes I've done here. Feel free to check out the code. So I'm just cloning the repo and using our model, right? And I've introduced an extra parameter called run debias. When the sentence scorer is running, whether we have to run without debias or run debias false or true. It's a simple boolean I've introduced, and then to make sure that the injected code is running appropriately. And as you can see, right, if I use a very well formed sentence and see, so what does MLM score basically gives is how well the model's embedding ability or expressivity or perplexity, whatever the number that comes to mind as a proxy for the quality of language model, you can imagine. That's exactly what we are trying to do by getting the pseudo log likelihood scores, right? So as you can see, when I'm running the first sentence, right, I would like to travel to Siberia and take the Trans-Siberian train. The log likelihood score, pseudo log likelihood score for a model for our sentence transformer without debiasing is minus 147, right? Remember, in pseudo log likelihood or log likelihood, higher is better. So 147 is higher, but if you run with debiased true, it is slightly lower, 148. So, but as you can see, I'm still trying to make the same point and same case here. It is the level to which the pseudo log likelihood is diluted or become as reduced is very, very negligible. So that is another proxy to indicate that the debiasing process using INLP has not sabotaged the quality of sentence embeddings, right? So we have proved it in two techniques. One is a vanilla similarity score with and without debias, and then MLM score with and without debias, right? So these two should tell you, should convince you at least INLP is aggressive. Nonetheless, in this particular example, it is not so bad, right? It does not sabotage the sentence quality. That's the proof. That's the key takeaway for you. One important thing, guys, this particular cell has errored out here, and the results, I have something to show to you guys, and I will make sure before we close this episode, I'll make sure that this is you get to see the results of this cell. But let me go with the flow and complete the thought process, right? So now that we have made sure, now we have understood that not only we are able to debias, we are also able to debias without affecting the model's ability, right? So that's pretty much what I wanted to cover, guys, right? So as promised in our agenda, feel free to check out both the repos. Like I said, right, it's not a simple change. At the same time, it's not a complex change. There needs to be some substantial changes required, right? You can compare the original repo and the fork to see what has been done. So in terms of exercises for the readers, like I said, right, we have done only INLP for the same model extended to run for the another debiasing technique called Sentence-Debias on the same Sentence-Debias technique on the same sentence transformer model, and compare the results with INLP and see which one is better, and also make sure that how much Sentence-Debias is affecting the quality of the embeddings. And I've included some FAQs and references why mean pooling is better. Rymers have answered for it. Feel free to check it out. And I told you guys, like, I'll show you what is the data set breakup of the 1 billion sentences that has been used for further pre-training sentence transformer. This is the breakup. As you can see, in the 1 billion, about 700 million is coming only from Reddit comments and Yahoo answers. These are some of the things, right? So I'm going to let you guys be the judge as to why a sentence transformer, even though it is like a compressed version, is having a lot more bias than a vanilla bird version. We could, my best guess, probably Reddit comments was not so great in terms of bias freeness. I don't know. I'm only in the realm of speculation here. Feel free to speculate or do some experiments. So like I said, this is the link to the dirty secrets of book corpus, and there's a dataset facts for how to highlighting the problems in the book corpus, right? The iterative null space projection that I've showed you, the INLP, that the concept of INLP and projecting your representations on the null subspace is originally from a paper called Null It Out. It's a phenomenal paper, and one of the authors is my favorite, Joe Goldberg. So feel free to check out. That's the first link here, and the research that I cited in this particular notebook and video is the second link. And the third link is pretty interesting. There is one more research, recent research called, both of these research are pretty recent, but auto debias is the most recent. It is an interesting take. They are saying that they can come up with some, they can synthetically come up with some automatic prompts to automatically fine tune the model and automatically debias, right? So that is something I would like to probably cover in a subsequent episode in connection with the same thing, right? Diagnosing and debiasing. But yeah, so that's what I'm mentioning here. So in terms of closing thoughts, this is something we can do. And one more thing, if you can notice, right, these tests are like very binary, right, like male, female and other things, but world has changed. We are in 2022. There is no not much of LGBTQ representations, right? So that is something you could see, and the test can be extended to be more inclusive. I think none of the techniques in benchmark like seat or stereo set or crowdsourced pairs, none of them are having this level of granularity when it comes to sexual orientation or gender. The link to the notebook is in the video description as usual, and then the code repos, like I said, I've given the link and feel free to check it out. And for the exercises, as usual, the answers will be available in the Slack channel, and 5 lucky participants will get laptop stickers. Yeah, that closes it. As promised, guys, one of the cells under INLP projection matrix creation errored out. I just wanted to make sure that you guys understand. Just to recap, I've brought in the Wikitext data down, and then we create the projection matrix or the subspace for a particular type of bias, which is gender here in this case, and then we give the base model. When you run the INLP projection matrix, what exactly happens, you can see from some of the info logs, right? So you can see it is extracting male sentences, female sentences, and neutral sentences to feed into the classifier. Obviously, for all practical purposes, it's completely balanced. It's about 10K each, and then they are running encoding male sentences using the sentence transformer model we have given, that is this, getting the representations for male, female and neutral, and then they are running it's iterative null projection, hence multiple classifiers, right? In this case, they are running 80 classifiers to get different matrices, different classifiers, get their learned weight matrix, get the null space for each and every matrix, do the intersection of null space, and come up with the projection matrix, and they save it here. So this is what is happening when you run the projection matrix code, and this is exactly what is used to debias the further sentence embeddings as we move forward. As promised, I just wanted to cover it here. So that's pretty much it, guys. I wanted to cover in this first episode of stuff you should know. And just to summarize, you have learned the intuition and concepts of how to diagnose bias in a brand new model, and then measure it empirically, and then pick and choose debiasing techniques based on the kind of model you have in hand and what you want to prove. Measure the bias again after debiasing it, compare it empirically speaking, and then also you should be able to demonstrate the fact that the idea of debiasing the model did not sabotage the model's power, right? So all these things have been covered. So with that said, that should be a wrap, and the code should be in the link, and feel free to participate in the quiz and share the answers in the Slack channel. And for 5 lucky participants, I'll give you a laptop sticker, and this is what I've got printed, the Diagnose type laptop stickers. And so that's pretty much what I wanted to cover, guys, and thanks for your time, and I'll see you guys in another episode.